All right, today we're talking about Chapter 8, Section 1. Again, the way we get to this particular part of our textbook, you're going to get to your math lab, you go to your assignments, and over here, we're going to do 8.1 today. We're not doing the homework, obviously, but we're going to go do 8.1. One moment. Okay, sorry about that. And these are all the things that they're little videos, little PowerPoint, but up here, again, there's a little book symbol. What we're going to do is we're just going to click that, and it's going to take us to our textbook and what we're talking about today. All right, so today we're talking about set theory. Their sets are very super duper important in mathematics, and there's an entire discipline based around set theory. The discipline that, believe it or not, is I mean, at the higher reaches is beyond my comprehension because it's not something I study. But what we're going to talk about today is sets, and it goes so much deeper than what we're going to see today. But this is just the introduction to it, right? So this obviously up here we can talk about what we actually let's go ahead and talk about that. I don't want to snip that actually. Let's not snip it. Okay, so right here. All right, a set is a collection of objects whose contents can be clearly determined. The objects in a set are called elements or members of the set. Right? A set must be well defined, meaning that its contents can be clearly determined. All right, so our methods for determining a set, this I will snip, and along with example 1. Alrighty, so an example of a set is a set of the days of the week, whose elements are Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Right. So capital letters are generally used to name sets. So in this particular case, we're going to name our set W. Right. Three methods are commonly used to designate a set. One method is a word description. We can describe sets W as a set of the days of the week. A second method is the roster method. That involves listing the elements of set inside a pair of braces. These braces, uh, they're just curly braces, and in mathematics, they mean a set. Okay, you're probably familiar with parentheses and brackets, right? Well, that's parentheses and brackets, right? This is different. These are curly braces, and they represent a set. Where are we at? All right. Well, basically what I just said. All right. So in this particular case, we called W the set of days of the week, right? So we named it W, right? W being the name, and then Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay, and of course we talked about the parentheses and square brackets. All right, we'll just go ahead and read that. So grouping symbols such as parentheses and square brackets are not used to represent sets. Only commas are used to separate the elements of a set. And again, the elements of a set are the individual pieces inside the set. Uh, Separators such as colons or semicolons are not used. Finally, the order in which the elements are listed in a set is not important, and we'll see more about that later. Thus, another way of expressing the set days of the week is, this particular way. Doesn't matter. One moment again. Sorry about that. So, doesn't really matter the order, and we'll see that later on. But let's look down here, example 1. So if we were to write a word description of the set, again, I just cut the solution because I feel like many of you would know. Um, we have the set's name is P, okay, and the set P has Washington, Adams, Jefferson, Madison, and Monroe. Okay, and for the record, I'll just like, oh, those are presidents. But of course, here it says they're the first 5 presidents, right? Alrighty, so next up we're going to do snip example 2. We're going to put it on the same page. I think they'll fit. Okay, so example 2 reads, The set C is a set of U.S. coins with a value of less than $1. Express this set using the roster method, right? And again, the roster method is the method where you write the name of the set, and then you write in brackets the elements of that set. So uh, the coins that are less than $1, penny, nickel, dime, quarter, and half dollar, right? So that is the U.S. coins. I wonder if we can put example 3 in there. Oh, okay, next up, this is pretty important. All right, the third method, because if you recall there was 3 methods, the third method is called the set builder notation. Okay, so starting over here on the left, the third method for representing a set is with set builder notation. Using this method, the set of days of the week can be expressed. Right now, I'm going to go ahead. I'm going to rewrite this. So, if you recall, we called the set of the days of the week. We called it W. Let's put it in green. We called it W. Right. That's what we called the name of the set for the days of the week. Right. So now we have to define what that set means. Okay. So we define it. We're going to say it's W is equal to what? Okay, so it's going to be equal to, we're going to do the same thing with curly braces here, right? we're going to have the opening curly brace, and we're going to denote the elements of the set. We're just going to call them X, okay? I believe in this section we don't go much further than that for right now anyways. We're just going to call them X, right? And then we're going to have a vertical line here, right? And that vertical line phonetically just means such that, okay? So what is X? What should X be? Well, X, as we see up here, is going to be the day of a week. All right. So we do this, we write that, and then we close the curly brace. So again, the second way, the roster method, if you recall, we would list something, comma, list something, comma, list something, and then we'd be done. Set builder is used quite often. Maybe not in this particular course or college algebra, but in pre-calculus we use it quite often, set builder notation, because in my opinion it's more precise, and we'll see that precision later on. Okay. All right, now here's some examples of going from the roster method to the set builder notation method. So here we have B is a set of members of the Beatles in 1963. Okay, so B is the name of the set, and it's it's the set of members of the Beatles in 1963. And of course we have George Harrison, John Lennon, Paul McCartney, and Ringo Starr. Okay, now that's the roster method. Set builder is just simply the B, right? Again, that's the name of the set. B is going to be equal to X, such that X was a member of the Beatles in 1963. Right? And that's really it. Same thing with S is the set of states whose name begins with letter A. We say S is equal to Alabama, Alaska, Arizona, Arkansas, right? Well, here we still using the same name S. That's going to be equal to X, such that X is going to be some U.S. state whose name begins with the letter A. Right. So, and then the third example here, again, I've just snipped a solution because it's not a brain teaser or anything. So express the set A being equal to X such that X is a month that begins with the letter M using the roster method. Okay. So what we're doing is we're going from set builder to roster. Okay. So all we have to do is just reuse the name A, and we just have to think, okay, so which months begin with the letter M? Well, okay, that's easy. It's March and May, and that's it. So example 3, we're going from set builder to roster, and I could probably snip 4. Let's see. Okay, so 4 doesn't talk about that. Okay, so next up. Alrighty, so start over here on the left side. The representation of some sets by the roster method can be rather long, right? So far we've seen examples of uh, the elements of a set, being five elements long, right? Or the size being 5 element, or the cardinal number, which we'll talk about later, having 5 elements, right? If we continue on, sorry. So the representation of some sets by the roster method can be rather long or even impossible. If we attempt to list every element, just a comma, Sherman. For example, consider the set of all lowercase letters of the English alphabet. If L is chosen as the name of the set, we can use set builder notation to represent L as the following. So we're going to call the set L for all the lowercase letters in the alphabet. And in set builder, we just say X such that X is a lowercase letter of the English alphabet. Right? Beneath that, a complete listing using the roster method is rather tedious, right? Same number L, but then we list every single element, right? Now this actually isn't too terrible, but I mean it would be rather tedious, wouldn't it? Right? So we can shorten the list. We can shorten the listing in the set of L by writing L is equal to A B C comma dot 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 comma Z. Okay, so we know those 3 dots. They're called ellipses, right? So what that indicates is that the elements in the set continue to in the same manner up to and including the last element Z. So many times you might have seen in mathematics mathematics, you might see ellipses meaning going on forever. Okay, and it does mean that. And as we see, it says it indicates that the elements in the set continues in the same manner. Okay, in this particular case, we're going from D comma dot 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 ellipsis comma Z. Okay, so I mean we're skipping writing all the letters E to Y. Okay, but in both of these cases, the point gets across, right? We know that this is obviously the precise way, but this is I dare say it, the lazy way, right? The lazy and quicker way of writing the set of all lowercase letters. Okay, next we're going to talk about the empty set. So consider the following sets. X such that X is a fawn that speaks. Okay, I don't really know too many fawns that speak. X such that X is a number greater than 10 and less than 4, which by the way, this fawn speaking thing, it has to do with the Blitzer, this Blitzer bonus talks about, I guess Alice, I forget. But that's where we get the fawn from. Anyways, X such that X is a number greater than 10 and less than 4, right? So can you see what these sets have in common? Okay, so let's real quickly. X such that X is a fawn that speaks. Okay, that there's no fawn that speaks. X such that X is a number greater than 10. Okay, cool, greater than 10 and less than 4. Okay, so it has to be greater than 10 and less than 4. Well, there's no number that's greater than 10 and less than 4, right? So that's what they have in common. Nothing, right? In both of these cases, there is not a set that defines these elements here. So there are no numbers that are both greater than 10 and also less than 4. Sets such as these contain no elements are called the empty set or the null set. Okay, now that's very important. So let's look at the empty set definition. The empty set, also called the null set, is a set that contains no elements. The empty set is represented by our curly braces with nothing in them, or a circle with a line drawn through it. Okay, so read down here real quick. Notice that the curly braces, the empty curly braces, and the circle with the line drawn through it, they have the same meaning. Okay, so that's 2 different notations for the same meaning. However, the empty set is not represented by putting the circle with the line drawn through it in the bracket. Okay, this notation represents a set containing the empty set. Okay, so things get kind of complicated pretty quickly when we start talking about sets. Also, and I know what you mean. I've had a couple students, and I think there's also a coach at Ball State, at least I've seen, because we have to sign for athletes, how many days they've missed. And I've seen a coach at Ball State, say the student has missed this many days. Okay. Now the thing is, I know what he means. You know what he means. He means 0. Okay. But in mathematics, that means the empty set. Now, if you put a circle with the line through it in my class, obviously at this point because we're online, things are a little bit different. But I wouldn't count you wrong. I would just say, hey, remember that means empty set. Okay, so in case you have a propensity to do that, I just kind of want to stop you right now. But like I said, I know what you mean. It's just depending on the context, it may be an incorrect solution. Okay, so example 4. Okay, this is one we can definitely not snip the solutions to. Okay, so example 4 reads, recognizing the empty set. So which one of the following is the empty set? Alrighty, so A, we have a set and it contains only one element. It contains the element 0. Okay, so how can I do this? Well, we'll just write. Okay, so A, it contains a set 0. Okay, so that set, it contains an element, all right, but that element is 0, yes, but that's not the same thing as the empty set. So A is not an empty set. So which of the following is an empty set? This is not an empty set. There, that'll do. Okay, so B, well, B isn't even representing a set. It's just representing a number, right? So this is also not going to be an empty set. Not an empty set. Okay. All right, C. All right, so this has potential, right? X such that X is a number less than 4 or greater than 10. Okay, so this is also going to not be an empty set. And let's examine why. All right, so let's reread this again. It says X is a number less than 4 or greater than 10. Well, previously we saw something like that, right? X is a number greater than 10 and less than 4, right? The number or the word "and" there makes a difference. In this particular on this page, there is no number that is greater than 10 and less than 4. There's no number that exists there. Okay. However, for this particular example, we do have something that exists. All right. It says X is a number less than 4 or greater than 10. Well, there are an infinite amount of numbers less than 4, right? 3, 2, 1, 0, -1, -2, -3, right? And there are an infinite amount of numbers that are greater than 10. Okay, 11, 12, all the way to infinity, right? So, unfortunately, C is also not an empty set. All right. Now, chances are, all three of these, the first three were not empty sets. So I bet D is going to be empty set. That's just the nature of how this is taught, right? So let's look at it. X such that X is a square with exactly 3 sides. Okay. Well, this is pretty obvious. There is no square with 3 sides, right? The very definition of a square is 3 sides. So D is indeed an empty set, right? So just to give you an idea of looking at the different notations, okay, A, again, the notation being the set is just contains the number 0. B is not even representing a set. C, you had to kind of think about it, but D is very obvious that it is indeed the empty set because there are no squares with exactly 3 sides. C, okay, so C, X is a number that is less than 4, okay? So what numbers are less than 4? Well, 3, 2, 1, 0, -1, right? There's an infinite amount of numbers that are less than 4, right? And then it says or, right? So X is going to be a number that's less than 4 or greater than 10. So it could be either, okay? And if you recall, and again, I really feel like this first example here kind of adds to the confusion, okay? Because it's wanting a number that is greater than 10 and less than 4, okay? Now, if we were to say, if we were to kind of change that up and we said greater than 4 and less than 10, well, then those numbers would be 5, 6, 7, 8, and 9. Okay, if we were to say greater than 4 and less than 10. All right, the operative word meaning and there, or the operative word and there means that both criteria um, must be abided by. Okay, so that's why this particular example on this page was indeed the empty set. There is not a number that is both greater than 10 and less than 4. There's not a number that's both of those. However, oh, for this one, x is a number that's less than 4 or greater than 10. So it doesn't really matter. We can choose a number that's less than 4 or a number that's greater than 10. And that's an infinite amount in both ways. Okay, does that help any? Hope it does. No, no problem. Alrighty, that was 4. I feel like we're missing something somewhere. Oh, I forget. this, Fred, I can't just scroll. Okay. All right, so let's start looking at the left over here. So the notations for set membership. All right, so we're going to introduce another notation here. Right. So we now consider two special notations that indicate whether or not a given object belongs to a set. The notations are going to be, and the way you write them, they're kind of small. I know, I'm sorry. Let's just, maybe I can make them a little bit larger. All right. So notations, when you write them on your paper, all right, this weird looking E right here, I usually just make a C and then I put a little line through it. And of course this one being not an element, I write my little C with the line and then I put a line through it like that. Okay. So what do these notations mean? So the symbol sideways E, this symbol is used to indicate that an object is in an element of a set. The symbol E is used to represent to replace the words is an element of. Okay, so this symbol just basically, like, you can just write that symbol instead of writing is an element of. All right, and on the other side, if I put a line through it, that means is not an element of a set. Okay, or is not an element of. There we go. All right, so two new notations for you. So let's do example 5. So determine whether each statement is true or false. Okay, so looking at at this, let's blow this up just a tad more. That actually helps, I bet, huh? Alrighty, so determine whether each statement is true or false. So R, this is reading, R is an element of A, B, C, D, E, F, G, H, I, J, K, all the elements, or all the alphabets, right? And they're all lowercase, okay? So it looks like A is indeed an element of that set. Okay, that is a true statement. B reads 7 is not an element of 1, 2, 3, 4, 5. Okay, well, it's very obvious that 7 is not an element of it, right? Because I mean, this particular set only has the elements 1 through 5. So it is true that 7 is not an element. All right, so that is also a true statement. Okay, C is saying the set A, okay, the set A is an element of the set A and B. This is kind of tricky, okay, because the set A is not in the set A, B, right? The element A is in there, but the set is not. Okay, and again, this has a little curly braces around it, so it's saying the set A is not in there. Okay, and again, that is obviously true because that particular set only has the element A and the element B, but not the set. Lots of words, right? Okay, so next up we have, let's see if I can make this larger. One second, I'm going to see if I can't make the text bigger. I did have a student say that they can't, they're having a hard time seeing it. So maybe that'll help with it, I don't know. But anyways, so these sets of natural numbers, right? So for much of the remainder of the section, we'll focus on the set of numbers used for counting, all right? So 1 to infinity. The set of counting numbers is also called the set of natural numbers. We represent this set by the boldface n. Okay, so real quickly, because I'm pretty sure we'll talk about more than just natural numbers in this particular course. Let's see why they're called natural numbers. Okay, so these numbers that go 1 all the way to infinity, they're called natural numbers because these are numbers that you can see naturally. These are the first numbers that one learns as a baby, right? Or as you know, humanity was starting out. These are numbers that we first thought of because you know you can't see -2 trees, right? You can't see 0 apples, but you can see a natural number, right? You can see 7 trees. You can't see 7 apples. All right, that's what they call natural numbers. Now it says that it's represented by the boldface letter N, right? If you were to write this on your paper, I mean you could if you want to, you know, kind of go like this, you know, and then like this, and then like this, you know, make it make it look like a Netflix logo. Or what I do is I just do 2 vertical lines and then like this, okay, and that represents N. And honestly, for every other text besides this one, and we probably will later on once we get into the course. This is the first semester I've ever taught this course, so I'm not entirely sure where we're going. But in every other mathematical text, that's how the natural numbers are represented. And not necessarily a bold letter, but kind of like what I just drew there, my Netflix logo. All right. So again, the set of natural numbers is the numbers 1 to infinity. The 3 dots are ellipses after the 5 indicates that there is no final element and that the listing goes on forever. Right? So let's go ahead and do example 6. So example 6 reads, express each of the following sets using the roster method. Okay, so the roster method, if you recall, is basically, you know, we put our curly brace and then we list out the elements. Okay, so let's do that. For A, set A is a set of natural numbers less than 5. Okay, so what we're going to do is we're going to say, okay, so the name of the set is A. Easy enough, okay? And it's going to be the natural numbers less than 5. So I'm going to list all the numbers less than 5. All right, it's saying less than 5, not less than or equal to. So my numbers are going to be strictly 1, 2, 3, and 4. Okay, those are all the numbers that are less than 5. Okay, set B is a set of natural numbers greater than or equal to 25. Okay, so this could get kind of messy, right? Except I'm not going to be writing 25 to 1,000 to 2,000. I'm not writing every number to infinity, right? I'm going to use the handy dandy ellipses. So B, okay, so set B is all the numbers that are greater than or equal to 25. So we're going to do 25, 26, and we'll do 27, and then dot, 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 and we'll close that bracket there. Let's fix our 7 up a little bit. Looks a little janky. Okay, so that's how we write all the natural numbers that are greater than or equal to 25. Okay, and then C reads E is going to be equal to the set X such that X is a natural number and X is even. Okay, so let's put C down here. We don't have to, I don't think. C, and it's going to be E, the name of the set is E. All right, it's going to be the set of, all right, again, let's read this. What does it say? It's saying X such that, again, that vertical line means such that X is an element of the natural numbers and X is even. So X is going to be a natural number. It's an element of the natural numbers and it's going to be even. Okay, so we're going to start with the number 2 and then go 4, 6, and I guess we can fit an 8 in there. Dot, dot, dot. Ooh, that's not a good dots. Okay, so the blackboard's not reading individual dots here. And then the curly brace there. Okay, so that is how we represent natural numbers. All right, so let's do this brief review of inequality notation, just in case, because I know many of you probably haven't taken mathematics in a good while, or if you have, you haven't thought about it because you don't care to. That's okay. I never cared about British literature either, but for some reason I had to take it. Shoot, which one did I end on? I forgot. All right, I'm just going to, hopefully it's this one. Ah, darn it. All right, so I copied the same one twice. That's okay. What we'll do is we'll just not talk about that one. All right. All right, so here we go. Oh, that's not what I wanted. All right, so inequality symbols. We know that if we just have that little caret to the left, we know that's less than. If we have the little caret to the left with a line underneath it, we know that's less than or equal to. If we have the caret to the right, that means greater than. If we have the caret to the right, it means greater than or equal to. All right. So you know if something is less than a, that it's it's less than a. Uh, um, and if it's less than or equal to a, we include the number a, right, in our notation. So let's go ahead and look at this. All right. So this is a less than a. So this is reading x such that x is an element of the natural numbers, and x is less than 4. Okay. So x has got to be less than 4. It cannot be equal to 4. And again, it's an element of the natural numbers. So the only numbers that are natural that are less than 4 are 1, 2, and 3. If we included the a, okay, so if we include the 4, then yes, we would include the 4 here. Same thing can be said for the greater thans or greater than or equal to's. The greater thans do not include the number. So again, x such that x is an element of natural numbers, and x is greater than 4, right? So all the numbers that are greater than 4 are 5, 6, 7, 8, dot, 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 all the way to infinity. We do not include number 4. But if it's greater than or equal to, then we do include number 4. Okay. Then over here, it wouldn't say slightly more complicated, but just a little more extra stuff, right? More extra. So we've got a is less than x is less than b. Well, that's basically saying is that x is between a and b, and not including a or b. So read over here, x such that x is a natural number. Okay. So and it's saying x is between 4 and 8, but we don't include 4 or 8 because it's just less than. So we'd say 5, 6, and 7. Okay. Down here, if we included them, okay, then what we would do, well, we would say, x is between 4 and 8, including 4 and 8. So we see that here. And then these last two examples are basically just kind of swapping them off, right? This one is a less than or equal to, and then we have a less than. We have a less than and a less than or equal to. So obviously, we would include the number a here, but not the b. We would include the number b here, but not the a. So we would have x such that x is an element of natural numbers, and 4 is less than or equal to x is less than 8. So this is saying that x is between 4 and 8. We can include 4 but not include 8. And we see that here. And down here we see that x is between 4 and 8. We don't include 4 but we include 8, and we see that here. Okay, so that's a brief review of inequality notation. Inequality notation. New page. Alrighty, so example 7 reads, express each of the following sets using the roster method. Okay, so we're going to be using the roster method, so we're going to be listing them out. Ooh, didn't want the thick one. A, right? So A reads x such that x is an element of natural number. Okay, so that's again that's just normal stuff, normal notation. All we're saying is that we're dealing with natural numbers. Okay, so if that notation kind of scares you, it's just understand that mathematics is very precise, and we have to be very super precise and say that x is a natural number because I don't know if you've heard, but like there are other types of numbers that we classify, like integers, rational numbers, real numbers, right? So we have to say natural numbers to denote that we're talking about whole numbers from 1 to infinity. So anyways, back to this. X such that x is a natural number, element of a natural number, and x is less than or equal to 100. Okay, so we need to figure out all the numbers that are less than or equal to 100 that are natural numbers. Well, we know that natural numbers start at 1, and then we go 2, and then 3, right? And then we can do comma, and I'm not gonna write all the way to 100, so I'm gonna do comma, dot, 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 comma, 100. Okay, and that's it. That basically is A, right? We expressed all the natural numbers that are less than or equal to 100. And then B, yes. Uh, no, it actually would not be wrong. Um, but no, it wouldn't be wrong. I was gonna say, but I mean the ellipsis, generally when we read things, we're reading up or away from zero. But no, it would not be wrong at all. Okay. B, and because, and this might be why you asked, early on we said that it doesn't matter the order of the elements in the set. So yeah, I mean you could start with 55, go down to 47, go up to 63. You can write them all if you want to. It doesn't matter the order as long as they're in the set. B reads x such that x is an element of a natural number, and x is going to be between the number 70 and 100. We're including the number 70, but we're not including the number 100. Okay, so what we're going to do is we're going to start. This is pretty funny. I used to, I had a, well, I'll just have to find the comic and show you. It's hard to explain. Sorry. This is one of those moments where you just kind of fast forward and go faster. So we're going to start at 70, and then we go to 71, and then 72. And again, I'm not in a hurry to write all the way to 100, so I'm going to do comma, dot, dot, dot. All right, but we're actually not going to 100 now, are we? Because in this particular problem, it says we are going to 100, but we're going to be strictly less than 100. Okay, so we're only going to be going to 99, comma, 99. Okay, and that was representing the set of natural numbers. I believe this might solve the issue of, yeah, because earlier they were a lot smaller. Um, and I'll go through before I upload the notes. I'll go through and blow them up a little bit. But I think doing this might solve the issue of it being a little too small. Anyways, starting from the top. So the cardinality in equivalent sets. The number of elements in a set is called the cardinal number or cardinality of the set. For example, the set AEIOU contains 5 elements and therefore has a cardinal number 5. We can also say that the set has a cardinality of 5. Okay, so the definition of a set's cardinal number. The cardinal number of a set represented by n, the n on the outside of the set's name. So in our definition, the set's name is A. So it's represented by n and A is a number of distinct elements in the set A. The symbol n to the A is read n of A. Okay, so we can go back and say, all right, so the cardinal number of set A represented by n of A is the number of distinct elements in the set A. Okay. So notice that the cardinal number of a set refers to the number of distinct or different elements in the set. Okay, so they have to be different elements. That the cardinal number has to be different elements, and we'll see an example down here. Maybe not. So repeating elements in a set neither adds new elements to the set nor changes its cardinality. For example, the set A being 357 and the set B being 355777 represents the same set with three distinct elements, 3, 5, and 7. Thus, the cardinality of A is 3 and the cardinality of B is also 3. Okay? So it doesn't matter if we repeat. We're only looking for distinct and unique elements when we discuss cardinality. Cardinality, that's a fun word. I don't get to say it enough. So find the cardinal number of each of the following sets. Okay, so A, well, that's pretty easy, right? 4, 7, 9, 11, 13. So that just has a cardinality of 4. So what I'm going to do, let me see how they want this. Okay, yeah, they're wanting us to write the entire notation out. So what we're going to do is we're going to say the cardinality, so we're going to say n of the set A is 4. Okay, and then B. All right, so B is a set just containing the number 0. So we're going to say the cardinality of B, all right, it only has one element, and that element's 0, so its cardinality is 1. C, it's 13, 14, 15, dot, 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 probably all the way to 21, to all the way to 23, okay? So if we have 13 to 23 and we're including 13, so that means there must be 11 elements in the set. Okay, so the cardinality of C is 11. And then D, we have the empty set. Okay, so the empty set contains no elements. There's nothing in it. Okay, so if there's nothing in the empty set, what do we call it? Okay, so we don't call it anything except the empty set. So the cardinality of the empty set is just going to be 0. Okay, and that's all you do. All we're doing is just counting distinct elements in a set. Um, oh, no, that's not good. Alrighty, so let's start from the top on the left over here. So sets that contain the same number of elements are said to be equivalent. That makes sense, right? If things are the same, then they're equivalent. So the definition of equivalent sets, set A is equivalent to set B means that set A and set B contain the same number of elements. For equivalent sets, the cardinality of A is going to be equal to the cardinality of B. All right, so here's an example of two sets. So set A is the set of vowels. A, E, I, O, U, and obviously we're not talking about sometimes Y here, just simply A, E, I, O, U. And then B, X such that X is an element of natural numbers, and it's between 3 and 7. Well, 3, 4, 5, 6, and 7. We see the cardinality of both A and B are 5. Okay, therefore we say that they're equivalent. We say that the sets can be placed in a one-to-one correspondence. Okay, so you see how the A corresponds with 3, E corresponds with 4, so on and so forth. All right, since we can take one arrow from one set and go to the other set, we call it a one-to-one correspondence. Okay, and again, as mentioned earlier, it doesn't matter the order whatsoever. Okay, it's just the fact that there are indeed 5. So the definition of a one-to-one correspondence and equivalent sets. If set A and set B can be placed in a one-to-one correspondence, then A is equivalent to B. The cardinality of A is equal to B. If set A and set B cannot be placed in one-to-one correspondence, then A is not equivalent to B. The cardinality of A is not equal to the cardinality of B. Okay. So let's look at example 9. So determine if the sets are equivalent. So figure 1 shows the top 5 impediment to academic performance for U.S. college students. So stress, sleep problems, illness, anxiety, and work. Well, I don't know if any of those are really my biggest impediment. Mine was basically maybe like laziness and video games. I don't know. I guess maybe sleep problems. I don't know. Anyways, y'all didn't ask, but now you know. So we're going to let A be the set of 5 impediments shown in figure 1. And B is going to be the set of percentages of college students. Okay, so are these sets equivalent? So first of all, let A equal to a set of 5 impediments shown in figure 1. All right, so it even says the set of 5 impediments. 1, 2, 3, 4, 5, okay? So set A has 5 elements. Okay, so set A has 5 elements. B is the set of percentage of college students reporting each impediment. So set B, and let's go ahead and write this out. So the cardinality, looks like an H, doesn't it? The cardinality of A, all right, is 5. Okay. The cardinality of B. Well, let's first write the set B, and let's write the elements in B. Okay. It's the set of a percentage of college students reporting impediments. So looks like 28% is one, 20% is another, 19% is another, 19% is another, and 14% is the last one. Okay. Oh, wrong notation. Is the last one. Okay. And again, all I did was, 28, 20, 19, 19, 14. Okay. Well, 19 is being repeated. Okay. So when I talk about the cardinality of B, I would say 1, 2, 3. Okay, I'm not going to count 19 again, and then 4. Okay. So the cardinality of B is going to be 4. So what that tells me is that these are not equivalent sets. So the cardinality of B is equal to 4. Excuse me. So they are not equivalent sets. That's pretty easy. Well, really easy. This is pretty funny. The percentage of Americans optimistic about the future. In the Northeast, they are not optimistic at all. Well, I wouldn't say not at all. It's just a lot lower, I guess. All right, so this we're talk about. This. We're gonna skip the thing about Aleph Null, mainly because I mean it's cool to know, and you can look at it in your textbook. You can read it in your textbook. But this talks about Aleph Null, and if you ever want to if you ever go down a mathematical rabbit hole on YouTube, talking about just infinities and the largest numbers and stuff, Aleph Null is definitely something you want to YouTube. And real quick, let me go back up and show you what I mean. Okay. Aleph Null right here. Okay. YouTube that, and you'll go down a crazy rabbit hole. Okay. Looks like we're almost at the end here. Okay, so let's go back here. So finite and infinite sets. So example 9 illustrated that to compare the cardinalities of two sets, pair off their elements. If there is not a one-to-one correspondence, the sets have different cardinalities and are not equivalent. Although this idea is obvious in the case of finite sets, some unusual conclusions emerge when dealing with infinite sets. And infinity is, I'm teaching an applied calculus course right now also, and I just got done telling my class that calculus is fun because we get to deal with and play with infinities. And hopefully, I might see some of you in that class later on. But playing with infinities is actually pretty cool. So finite sets and infinite sets. So set A is a finite set if the cardinality of A is equal to 0, that is, it's an empty set, or if the cardinality of A is a natural number. All right. So basically, if we can put a number on the cardinality, a set whose cardinality is not 0 or a natural number is called an infinite set. Okay. So equal sets. We conclude this section with another important concept of set theory. equality of sets. So definition of equality of sets. So set A is equal to set B means that set A and set B contain exactly the same elements regardless of order or possible repetition of elements. We symbolize the equality of a set A and B using the statement A is equal to B. Okay, so for example, if A is equal to WXYZ, okay, that's in order, right? And B, in our alphabetical order, and B is ZYWX, then we can say that A is equal to B because the two sets contain exactly the same elements. They might be rearranged in some way, but they are the exact same. Okay, and uh, this basically just kind of um, hammers the point in even more. And we can go to example 10. So this reads, determine whether each statement is true or false. Okay, so is 489, is that equal to 894? Okay, well, we have 8s in both, 4 in both, and 9 in both. Okay, so these sets, they are equal. Okay, so it is going to be true. All right, B, I mean, this is pretty obvious, right? 1, 3, and 5. And then is that equal to 0, 1, 3, 5? Well, obviously not, right? They don't have this. They don't have the exact same elements. The cardinalities are different, so these are not equivalent. Okay. And I believe that did conclude. Yeah, that does conclude today's lecture.